Alright, we're gonna get into this. Let's adjust some settings here, and it's SDF 13 and anti-alias frame. So I'm not sure if we're doing anti-aliasing or not, but we got to figure out where the artifacts are. So, all right. So we're about ready. Okay, there we go. Okay. So let's get this going. Right now, you'll kind of see this weird kind of thing in the up here, and that's just me kind of like taking a break to have some fun and trying the cylindrical camera setting. And we're gonna uncomment that. Well, we're gonna get rid of that right now. So we see these camera types. So OGP for orthographic projection. T3I for tube, three-dimensional, and inner. So we create a tube, and then the rays are looking into the tube, right? And then this T3O is the same thing. It's a tube, but it is looking outward. And then AAZ means aligned on axis Z. So this is a tube that is aligned on the Z-axis, so you could think of it as a big Z-axis tube, and it's being used as a camera, right? The orthographic projection top is the simplest, right? So if we really quickly comment out all of these, and let's go back to orthographic projection top to show you what that looks like. It's not what we're going to stick with, though, but let's just make sure that you know that works, right? Let's have a little sanity check. So orthographic projection top, that's what I'm expecting. We have some dollying action in our projection still, in our camera. That's fine. And let's look at the three-dimensional view. So the 3/4 downward view. So this is orthographic projection, 3/4D for 3/4 downward, meaning that it's a 3/4 view, but we're looking down on the model, right? And then eventually we might want a 3/4 upward view, which will be like 34U, but let's just use this for now. So let's save this and give that a run in our shader toy over to the right. And okay, so that's what I expected. Now, the problem with this camera right now is we can see these big, like, artifact nubs, and it's like, what the heck is going on there? It almost looks, it looks like it's so off that it's more than just an anti-aliasing mistake. Like, somewhere I think we've made a mistake as to figuring out which voxel we are inside of. Like, we've gotten that math off by a significant amount. And one way to kind of figure that out is we need to zoom the camera in even more. And if we zoom the camera in even more, we can probably figure out if this is like, is this just an anti-aliasing artifact that's just really out of control? So like right here, these little nubs, are these nubs anti-aliasing problems, or are they something worse? And I think unfortunately, I think they are something much worse, and so we have to figure out, you know, why do we have these, right? And it looks like it appears on every single cube. Also, like, what's with that? That's a little artifact, right? Like the little flickering. So a lot of just weird things going on here. And so let's just look for the keyword zoom, because I think that we have that. So zoom in camera, right? And if it's 1, we're just doing this, but that's not really what we should do. We should really actually add a some type of scale factor to this. So what I think it should be is we're gonna take a non-zoomed in camera, and then we want to we just want to take the H. What the hell does H stand for? HW. So H width and H height. I'm not sure why I called that H, because that's kind of a weird name to call it. Float HW and... Okay, so we have this, Oh, it's called halfway. It's halfway, right? Halfway. Yeah, that's what it is. So, HW, halfway width. And then this is halfway height. HH is halfway height. And then while we're here, we could, since that's a thing, let's go here. HH means, do we have a definition for that? Nope, doesn't look like we do. And HH means. So if we have a H and H, we'll do halfway height. And HW means now, maybe a little reference for, you know, where the file we can find it. There we go. That'll just help us maybe in the future, next time we see a variable like that. HH means and HW means. Okay. So, right, because we have the I resolution divided by 2, and the Y divided by 2. So in order to zoom in, we just want to do like H W equals HW, and then divided by some type of zoom factor, or multiplied by a zoom factor, right? Now, I think that the more zoomed in, the larger the zoom number, I feel like the... If we multiply by 2, if we have the number 2, I think we should be zoomed twice in. So, zoom amount... zoom, and it's kind of a zoom factor, even though it's a divisor. I don't know. It's actually like a zoom multiple, but it's like HH equals, HH divided by... So if we want a 2 times zoom, right, we're gonna divide by 2. And then the plane that we're mapping to becomes smaller. And if the plane we're mapping to becomes smaller, that means the objects are going to appear bigger, if that makes any sense. So with the zoom multiple, we'll just say, I don't know, define zoom multiple, and we'll just set it to, like, I don't know, 4. And then, you know, in some of these places where we're using defines, we really don't have to be using defines. And the consistency for, like, why do I want to use a define in some places and some places I don't, I honestly can't tell you why I choose one over the other. So I have some inconsistency there. Let's not worry about that. So zoomed in camera, and we are using the zoomed in camera. So, yeah, let's just do that. So let's take that and kind of run with it. See if we made any mistakes. Probably did. Oh, I guess I didn't. And running this, it looks like we're actually slightly zoomed out. So I guess the my guess was not as intuitive as I thought. So let's just try 8 and see how zoomed in that gets. And we want these to get a little bit bigger. Okay, so I'm noticing that we still have these really big artifacts, and it looks like the artifacts are getting bigger. Now, if the artifacts are getting bigger, does that mean it's more than an anti-aliasing problem? We try to do all our math with, like, pixels as the base unit, so we got to think about how is that affecting our code. Is that creating... Is trying to do all our math in pixels making the... like, are these actually highly exaggerated anti-aliasing effects because we try to do everything in terms of pixels, right? So this little edge here, what if this little edge here is really just 1 pixel, but we've zoomed in, so now we can kind of, like, see the problem. So I think this is actually a 1 pixel kind of problem. And the way we can try to fix this is we can change our settings to, like, trying to figure out what this edge case is. I bet if we... So let's go back to, like, 8 for our zoom here. Okay, so going back to 8, we have these little artifacts. Let me make sure that we're actually recording and that I can be heard. Okay, yep, so that's working. So I think these artifacts are 1 pixel artifacts, but they're not 1 pixel artifacts in the terms of an anti-aliasing problem. They have to do with getting the calculations for the closest voxel, like, off by 1 at the boundaries. And that is my hypothesis. And the way we could probably test this is we could start to shade different regions of the voxel. Right? We could, this cyan voxel, we could start to give it, like, a checker shading based on the number of pixels in the voxel. And then we could change the number of pixels in that voxel. So what I mean here is, right now, each one of our voxels is 16 by 16 by 16, and if we mess with this and also try to create some shading based on that, I think we're going to be able to detect the problem. So let's take a shot at that. So first thing I'm going to do is I'm going to save and I'm going to rerun just to make sure that I didn't screw anything up. Okay, so that's still good. Now the next thing is I'm going to do the absolute edge case thing here. And the number of pixels in each voxel, I'm just going to set them, instead of 16, I'm going to set them to 1. And that is going to probably completely destroy our day. So if our math is kosher, if our math is good, then this won't create a problem. But if we are kind of like have some type of weird off by 1 error, we might see the artifacts we might see some really bad stuff. So let's so that's actually not bad. That kind of makes sense, right? Because by making every tile just 1 pixel large, it also changes the that zoom factor. So let's go look at that zoom for a second and try to make a consistent zoom by altering the zoom based on the size of a pixel. So how are we going to make something that kind of doesn't change when we change the size of that okay, so what we're gonna do is we're gonna say F32 zoom multiple. Or let's just call it zoom divider, because we're using it to divide, so let's not confuse ourselves. Zoom divider. Zoom divider. And actually, we could do a F32 so we could actually have a factor, which could be the 8.0. Do we want to call it mul, or do we want to call it fac? I think multiple makes more sense to me than factor, just because factor could be like factoring, and factor is just a stranger, less common word than multiple or multiplier. And so let's try to make the language as clear as possible. So I'm going to take that zoo mul and zoo and just zoo mul. So that's what we're going to use in our shortcuts. And then mul zoo. If we do it backwards, use zoo mul. Right? And then also, what does that mean? So zoo mul means and zoomul is zoom multiplier. Okay. And we also have the zoom divider, zoodiv, and zoodiv. And yeah, this is kind of like a tedious, very time-consuming thing, but the idea is that I want to eliminate mental search space in my code for variable names, so I don't have to like I don't want to have to be like, did I spell it this way or that way or that way? So that way we use this very terse language, so that we eliminate the ways we could spell the variable. And also, if we always use this exact variable for a zoom multiplier, we can now find the zoom multiplier in all future code bases by just searching for this one exact term, right? Rather than all these different things that it could be called, we can just search for exactly this and always find it. What was the other benefit of doing this? So if we do it exactly, we're going to do a zoo div. Oh, and did we... So for zoom multiplier, if you type it exactly correct, we want a little notification that we typed it correctly. Like if we were trying to memorize it and we want to double check that we have the correct spelling in mind, we'll do that. And then backwards, so div zoo, and div zoo. We'll do backwards, use zoodiv, right? And then also, what does zoodiv mean? So zoodiv means zoodiv, zoom divisor, right? Okay. So now, with that, we have one more thing. We have the zoom factor. So zoofac, which we're not going to use. Don't you... And then if we use fac zoo, so backwards and big words, okay. So now we have a way to like find this stuff later, right? We could also, yeah. So we're good there. And CSDF 013, right? And we could make a little reference of what code base we first used this in, and that'll kind of help us if we want to actually find the usage case later. Okay, so now that we have that, and we've kind of like taken way too much time to do that, we can look at this zoom divisor and zoom multiplier. So so actually the zoom multiplier is going to be equal to, we'll say 8.0, and then for the divisor, we'll take like the zoom multiplier, and we will divide by the size of the number of pixels. So NP So we're gonna do like NP for a number of pixels, and then F32 NP equals the max of NP. I know we've done this before, so let's just Control F here and look for NPX. Yeah, so here we've kind of done it before. So I don't care about that, but we care about the number of pixels here. So that right there. So let's take this code right here, and let's just shove it in here. So we don't need all this. Well, float and max, actually we do need that. And number of tiles, number of pixels is the only thing we need. So let's get rid of this, and let's get rid of that. So the number of pixels is equal to the max of NPX, NPY, and NPZ. So that is kind of like... so we've used this kind of snippet in more than one place, so it might be good to create a function. And what would we call that function? I think we would call it like well, it's integers first. These are integers, so we could say U32. So I'm going to consider these uint32 values. Actually, no, we'll probably need a cast if we do that. So we're going to do I32 Yeah, this is why we don't do this, because we just get these long things. We could call it, get max F32, and then, we could do that, right? We could do get number of pixels, use npx, npy, npz. We could do that and be kind of like, instead of make some type of generic function, we could just kind of create a function that has the exact use case in mind. And but this is already, you know, npx, npy, npz. This is already kind of like, you know, this is already kind of verbose. It's like, have we really saved much doing this, or have we just increased the surface area of our code? And so you have to think about, well, is this readable? And you might be like, that's not readable. Like, that's not English. That's so terse. I don't understand, right? Well, get this thing, which we're going to use npx, npy, npz, get number of pixels. And instead of npx, we could do npm, right? Number of pixels max, right? And, you know, I kind of like that, so let's do that. So we're going to take all of this, and we're going to go... so this is a first-degree function, so that makes what we're doing kind of a second-degree function. Let's not worry about exactly where everything is in terms of its ordering, because I just don't think... I think it's going to be difficult to be more granular than first degree, second degree, etc. So let's not do that. But from here, let's just say that we'll just declare the function, right? So max of 3 with specific named by use case. So this is kind of like an explanation of the function, and the explanation of the function may not be the exact name of the function, but something that gives us a little bit more insight. So the idea is that we're going to call it this, just to give it the just so that we have... I want to avoid being abstract in our code. So even though this function really is get the max of 3 integers and return that max value as a float, right? It's a function kind of like that. But first of all, that's very wordy, and even if we could kind of like figure out a less wordy name for what's going on in a general sense, It's going to be easier to follow the code if we use a concrete use case for this function, right? So what we're going to do is we're going to say I32 npx. I will say define npx. Can't be I'm not sure what I'm gonna do with this. So what we could do is, what do I have on my clipboard? This. Let's get rid of that. So what I do like to do is kind of like do this staggering, so I can see them line up: npx, npy, npz. And the other thing we want to do here is declared I32 for ease of so a little note, I32, so you don't need to cast when calling this, actually U32 values. So in our code, we want to assume that the number of tiles on X, Y, and Z should never be negative, right? They shouldn't even be 0. So, but we're going to use integers because without a define like a define whatever and 1, this is going to default to integer, this defaults to float. And because of that, we cannot, if we do unsigned 32, we're going to have to cast each one of these parameters when we call it. That's going to be a pain in the ass, so we want to keep it as simple as possible here. So let's take this code that we already know works, and let's just paste it on in there. So F for float. Now we could get rid of some of the terseness now that it's in its own function. So we could actually remove that, right? And we could do, well, actually no, it's just gonna, I think it's better terse like this, just because we can see npx, npy, npz, and we can see where max is called in both spaces. So actually I do like it that way. I think that is the easiest to understand, rather than trying to decondense this and make it span multiple lines. I find that was usually harder to read. So, and it's not a problem to use like really short macro names as long as they're declared in a very small scope, right? They're declared right next to where they're used, and once you use them, you clean up after yourself in undefined. So that's fine there. So let's take that. And we have to also do this, and then we need return and then npm. Also, stylistically, the way I've been doing this is the defines I've been putting on these section headers related to the... We should probably keep that consistent style. So the defines are kind of like in this section heading area, and that kind of creates a kind of a thicker divider between the two functions. And also, if we want to reorder things in here, we don't have to worry about these being defined or undefined too early or too late. So let's take that, and then let's also make a note of what npm is. So npm is number of pixels max Okay, so that's what, so we have npx, npy, and npz, and npm is the max of all of those. And I think that is good enough for me. And then we can also go over here, and we might get some node stuff when we do this, but let's see, npm means non-pointer member. So npm means O2, npm means SDF. npm. So obviously when you have very short variable names, you're going to have collisions once in a while, right? You're going to pigeonhole yourself. And so let's say SDF013 for reference, and let's continue. So that looks good to me. I could have made a mistake somewhere, but let's not worry too much about it. Let's look for where that's called now. And we're going to use these integers, and we're going to get the max of all of those, right? And if the number of pixels in a tile is roughly equal to 1, right? Like if we're assuming if the voxels are completely square, well, we're going to just take this zoom multiplier and we're going to divide it by that, right? So if the number of pixels in a tile is just 1, we divide this multiplier by 1. Now, let's say that there are... so this is, say, 8 divided by 1, right? And so we still get 8. Now, and so we're still kind of like really zoomed in. Now let's say that the number of pixels in a tile, let's say it's 16, or no, let's say this is 8. So we take 8 and we divide by 8, and now we get 1. So now this divisor is 1. Now, does that make sense? Like, is this... So the idea is to have this value here kind of like stabilize the multiplier, so that this multiplier always results in the same amount of zoom, no matter the number of pixels in something. So, let's think about a tile map that's just one voxel. And the voxel is just 1 pixel, and we want to zoom in 8 times on that 1 pixel. So we're looking at that 1 pixel voxel, and we're going to zoom in on it, and we want it, this zoom multiplier, we're going to make that 1 pixel look like 8, right? Okay, so that makes sense. Now, if the number of pixels in our voxel was 8, then we still want that voxel to... We want all 8 of those coordinates to fill a single zoomed in area. So we're going to take this, and we're going to take that zoom multiplier, and we're going to divide by 8. Yeah, I think that makes sense. So in the end, we just got to try it out and make sure that it looks stable to us. So let's take this. Let's take this, and if we're correct with our assumptions, the size of the model just won't change after we change the If we change the number of pixels in a voxel, we won't see the we won't see anything change, is what we're looking for. So where the hell did I make a mistake now? Zoomol is a mistake. Syntax error. Okay, well, why is zoomol a mistake? So, oh yeah, because I don't even know why we wrote it that way. Okay, so write it like that, and let's try that. Okay, so now that we have that, let's go back up here, and we're gonna try to make this like, if we change this back to like 16, and see how that works. And we might have this math inverted. We're about to see if my logic is correct. So, okay, so that's still roughly the same. We still have something that's roughly the same size, so I would say that we have that kind of correct. The idea is that if we don't zoom at all, that one voxel is going to be 1 pixel. So it's going to be like really, really show up really small. Is that how we want it to be? 1 voxel is... Well, this is the zoomed in camera here. So we're kind of being a little bit... So we're doing our math a little bit differently. Because what we really want is... We would really like something where... We need some type of non-zoomed value for a voxel, and I guess if we're gonna do this zoomed, it's just a little bit confusing because it's kind of going to assume that if we're not zoomed at all, that like every single tile, every single voxel is just 1 pixel, I think. Yeah. Display size of a single voxel in terms of pixels, frags. So this is what this value ends up being. You know, I'm okay with that, so let's just say, I don't know, let's do 16.0. And let's just try to get something decently large. And, okay, yeah. Let's try 32. Okay, and now the next thing is... Now let's try 64. Okay, how about 128? 128? Okay, and if we run it, okay, so we have those artifacts again. So the next thing I want to do is I want to make absolutely sure that if we go up here and we change the size of this to, say, 1, that we're still going to get it displaying the same on the screen. So the idea is that the voxels will show up the same size. When we're using the zoomed-in camera, it's going to show the voxels at a consistent size no matter what the actual resolution inside of the voxel is. So let's run that. And I'd say that that we didn't quite get what I was expecting. So we got something interesting. It seems that we have lost one of our axes. by making that 1, it almost looks like completely two-dimensional. It looks like all of our shapes have absolutely no thickness. So I think we're stumbling onto something. I think that, okay, so let's go 16, right? But the size hasn't changed. So I think we're observing more of these little corner artifacts. Like something is causing these little corner artifacts. And I think it's some weird off by 1 error. And I think as we tweak with these values, it'll help us figure out what that problem is. So I bet if we make this value like 64, I bet we're still gonna have these voxels at about the right size, but I bet the artifacts are gonna get smaller. That's just my hypothesis. Hypothesis is if the number of pixels in the tile becomes larger, we're going to have smaller artifacts on these little corners. That's my hypothesis. My other hypothesis is that these voxel sizes will be the same size. So let's run this and check the assumption. And the assumption looks pretty correct. Voxels are the same size, and the artifacts are much smaller. So that's good, but that gives us a clue as to what's going on. And I also noticed that the little gray pattern here, it has this little border here, these little lines where there's definitely a distinct border between these shaded regions. And I bet the thickness of these little borders probably is the same size as the artifacts on the edges. Yeah, roughly, yeah, I would say roughly speaking, the little artifacts that are on the corners of every single voxel here kind of reflect the background pattern. And the background pattern is just roughly telling us how far back we ray traced until we gave up. And so the lighter means that we didn't go as far back, and then the darker means further back. So I was like thinking that if you go off into outer space, it gets darker and darker and darker. So that's kind of like how I made that shading from previous. Okay, so we have some good clues here as to like what is going wrong. And we did good with that camera. So let's take this and let's put it at like 8, right? So if we do it at 8, and let's see if we can get those artifacts to be a lot larger. Right, so our goal is just to test that hypothesis. And yeah, so if we make this 8, holy crap, those artifacts are really big. And so you know the problem we're having is not just it's not anti-aliasing, right? Anti-aliasing is definitely something we want to figure out eventually, but it looks like the grossest offense that we're having here is not because of anti-aliasing. It's some type of off by 1 error, probably something to do with our bounding calculation is off by 1, because off by 1 might not usually look like such a big problem, but remember that since we're trying to do all of our native calculations in pixel units, and our voxel is only 8 by 8 by 8 pixels, and then when we zoom into our voxel to show it really large on screen, if we're off by 1 on our calculation, we're going to see these really large mistakes. But that's actually, I would say that's actually more of a blessing than a curse, because if we did the math in a different way and we tried to use kind of like the standard voxel approach with floating point for everything, we might still be getting these off by 1s, but we wouldn't notice them because they would be at the pixel level always, or maybe at even the sub-pixel level. So you'd have the off by 1s, but they wouldn't be noticeable because of the way we interpreted the math. So I think by trying to do all the math with these very discrete units, I think it's going to enable us to make better quality voxels than we would otherwise. So what we're going to do here now is we're gonna actually pump this down. We're gonna pump it down to 4, and we're gonna see what happens. And 4, I'm gonna say, might be like a breaking point, because there's because every single pixel is now on a border with 4. So if we look at that, is that 4? Yeah, I think that's 4. So every single pixel is on a border. So it looks like to me that the problem is not on all the edges, but it's on one of the extreme edges. So I would say that this almost looks like, if we're kind of looking at it, if I take a guess, I'm gonna guess that it's like that this little artifact is 1/4 of our problem, right? So I'm gonna guess if we make this like a 3, the artifact is gonna be like 1/3 of the voxel, right? And if we do, say, half, if we do 2, right? Remember how we got rid of the entire thickness when we did 1? Well, that's because the entire voxel became an artifact. So if we do that, yeah, so now we got this really weird thing where half of the shape is now an artifact. And now it's very hard to see what's going on, because like half of our shapes, half of the plane is an artifact, if that makes sense. So we kind of know the basics of like what our problem is, and we need to kind of like oh god, figure out where that math is going wrong. And honestly, I don't know exactly where this math is going wrong. I think that this is going to be kind of difficult for us to figure out. I think the first thing we need to do is add color coding to the different sections of the voxel. Make some type of checker pattern inside of the voxel to identify what cell of the voxel we're in, what pixel of each voxel we're in. So let's pump this back up to 16, and we're going to figure out how we can create a checker pattern inside our voxels. And that checker pattern will give us some more feedback as to what is going wrong here, right? So we can actually checker this side, like light and dark checkers, so we can see the resolution of the voxel. That will give us some feedback as to what's going on these edges, especially if we do we'll need some type of different pattern for the bottoms and for the tops to make sure that we can tell, like, where the hell is this artifact? Is this artifact a bottom edge, or is it like a top edge, right? Like, I don't know. So let's figure that out. So I'm gonna turn the okay, I'm gonna just we're going to okay, we're gonna switch the volume here, turn on some music, and just try to figure this out. Alright, let's take some time to think this out. Make sure that we're doing this correctly. So, this is a similar formula that we used for the tiles, but now it's just abstracted towards the pixels. So, the first thing we need to do is we need to get a two-dimensional index. So we're just going to look at our pixel coordinates as if there's only an x and a y, and get an index for just that value, right? So this is going to kind of create the index that locates the x and the y on the last slice of the voxel, right? So we're thinking of the voxel as a whole bunch of z cross-sections, where each cross-section is a normal bitmap with an x and a y, right? So, hold on. So if we're doing that, then there should only be x's and y's in this calculation here, right? So the number of pixels on the x, otherwise known as the width, multiplied by the y will get us how many full rows of pixels we have. If the pixel y value is 0, then this ends up being 0, right? Because on the first row, we haven't filled up anything, and we only have a remainder of this x value, right? So this formula looks right for the two-dimensional index. Then the two-dimensional index is also seen as a remainder when we're stacking together cross-sections to get the three-dimensional index. So the math for this and this are very similar. This time you take how many cross-sections down you have, how many full cross-sections do you have, multiplied by the number of pixels in one cross-section, which is the width times the height, or the number of pixels x times the number of pixels y. Alright, so the volume of one layer of the cross-section, or the area of one layer of the cross-section, multiplied by how many cross-sections. That's going to give us the total amount of filled cross-sections, and then we just tack on the remainder with this dex 2D to get the final three-dimensional index of the pixel within the current voxel, right? So this pixel index will be a local index within the voxel. So that formula looks correct to me, and I've explained it. Now let's just do a quick sanity check and make sure that all of our x's and our y's and our z's, they kind of like all match up in the way that we expect them to, right? So just a quick sanity check, and we see that all these colors match. We see that x is same color, x times y. Okay, we already validated that formula, but we don't see anything that looks like out of place, right? Yeah, nothing looks out of place here. Now maybe we want to color all of our indices like a purple. And all of our indices are making sense, I think. Okay, yeah, so that looks good to me. I think that formula is correct. Now, there is the problem where maybe I have these are incorrect. So, for instance, I think tile X is these are integers, so I think this math should still work here. I think all the math is correct, so we're going to hope that when we rerun this, we don't get any syntax mistakes, because we've looked at it thoroughly enough that if we get a syntax mistake, it means that we haven't looked at it as thoroughly as we thought. And this looks like to be the case. So it is float and int. So we're mixing float and int. So that makes sense. This xyz.x. We have a problem where these coordinates could potentially lie in a subpixel area, right? And if that's gonna happen, how are we gonna solve that, right? How are we gonna, if we're on a subpixel, how are we gonna solve the problem? So it looks like floor xyz.x. So because our math is flooring the calculation here, I'm going to say the way we want to do it is so I think the most distinctive way to figure this out would be to I think we need an xyz.x variable and a y variable and a z variable, and so there could be a problem with our math. So the off by 1 error could be we have to figure out where rounding this makes sense. So as far as tile X, it kind of makes sense that this XYZ variable, these need to be in a discrete location before we start doing this kind of math. So I already see a problem where artifacts could be happening. So when we're looking at this, I think we need to take does it make sense to floor it, or does it make sense to find the nearest? So I think there's a round function in GLSL, so let's find round GLSL. So I think there's a round function, because really you want to take whatever's closest. And I think round... Yeah, so I think we want to use round for this, and it's something we're going to use in other calculations, but let's just fix the code first, and then we will address the problem. So it's an I32, and we're going to round, right? So we're going to round these values to calculate the integer value that it should be at, and then we'll do this math here. So let's save that, and because we just want to get everything running again. And then after we've got it running again, we can try to address some of the other problems here. So first of all, I think that, I don't know if that's what is causing our artifacts, but that's definitely something where we have to decide on. So we're going to say that we're going to say, so should it still be a float? So I think it would make more sense to be an integer, because here we're doing kind of a, well, actually no, because with the division, we're still going to need floating point accuracy before we floor it. So we're going to make a variable called f32rx equals round xyz.x f32ry equals around xyz dot y. All right, so a lot of the stuff you might be like, well, you know, you should just call it, you know, r.x, r.y, r.z, right? Because then, because maybe you could definitely make the argument that our shader code is 3 times longer than it needs to be because we've done it like this, and also we have a lot of potential for making transposition errors, just because we decided to like write it out like this, right? So is this a bad idea? The thing I like about having a variable like this is we'll never be able to write it like this. So if we had it like r.x, we could potentially write it like r.x or r.x like that, and then when you're trying to search for it, you might not find it because you did like a simple search rather than figuring out the regex for searching for r any amount of space dot x. Right now you shouldn't write code like that, but you know, you could make that mistake. So because I want to always be able to find these tokens in the code, that's kind of why I write them like that, right? Because if I'm searching for this, well, what if I did that, right? And now we can't find it, right? So obviously that's why you wouldn't want to write it like that, so you can actually find it when you're looking for it. But to prevent that from ever being able to happen, if I just make the components like this, then I'll never have that problem. So we're going to round, and we're going to make sure this runs, and then we're going to add the rounding calculation in, and we'll just see what happens to these artifacts, because that might actually change the artifacts, and we may have inadvertently solved the problem already. But we want to make sure... so if this changes what we get, it's not a... Let's just see what happens. So we have this. Okay, so we're about to... Let's pause it really quick. So if we pause it and we rerun it, do we get a change? Yes, we definitely get a change. So, so it does have something to do with how we are calculating the what voxel we're in now. Okay, so now we have to think about, now, should we be using a round, or should we be using something else? Because I'll tell you what, the artifacts look a lot worse now. But we're on to something. We've definitely figured out that, you know, part of the problem is that lack of it's part of the equation here is definitely doing that to us. So now we can try to figure out, well, is that how we want to solve it? How do we want to solve this, right? Like, we're on to something. How do we solve? Um, and I'm not sure. I'm not sure how we want to do this. Is that the correct approach? What is going to be more mathematically correct here? Um, do we really want to round and lose precision before we, because it looks worse. So man, when it looks worse, that is kind of, I could be wrong, but instinctually I want to say, oh, if it looks worse, then the math is probably worse, which might not be the right assumption here. Um, so I'm going to draw some stuff out and try to think about the math here, and think about, should we be, we're going to try to figure out what is more correct. Okay, so I've done a little sketching here, and I kind of figured something out here. So let's back to our code here, and we can do instead of Rx, we can do floor x. Right, floor. And the idea is we're gonna just make sure that everything looks the same still, make sure we didn't make any syntax errors. So we're thinking that this should be fx, fy, and fz for floor. So okay. So let's try that. We'll just put an F. And our hopes are that if we understand what we're doing here, that that we'll get the same result from when we reload this shader, right? Or maybe we'll get something better. Okay, so we got pretty much the same result. So that's good. That tells us that our assumption for how that math works is I think we're on to something there with how we do the math. So I'm going to keep that for now with the floor x, floor y, floor z. And we still got to look at where else we are using x, y, and z. So p is also x, y, z value. So x, y, z. So we do this p dot whatever, p dot x. So there's some potential here for there's definitely some potential here for some mistakes, for some off by one problems. So we'll definitely have to look at this, right? This is where we're calculating what voxel we're in, right? So I mean, it's definitely somewhere in this, right? So there's no flooring here, right? So there's this p dot x, so this might need to be the rounded x, y, z. We could try that really quick. So let's try to change this to... Yeah, so let's try, instead of p.x, let's try the rounded x and yz, and just see what that looks like, and see, you know, maybe it makes it worse, maybe it actually fixes it, and we're done, right? And rounded x is probably, bx is probably like a integer value, maybe? No? Okay, then what's the problem? Oh, Rx, Ry, so those are undeclared identifiers. So how do we get those to be undeclared? Oh yeah, because we're not using rounded x, we're using the float, the floored x, floored y, floored z. That's the values. So let's plug that in. I would say that might actually be more correct. It's definitely more consistent. And you gotta think, if these are like three-dimensional pixels in 3D space, and we're at a 3/4 view, and we're trying to like view each voxel, that actually makes sense that the edges, because we're trying to look at each single pixel, but the thing is, with that perspective, doesn't quite make sense with that perspective. I mean, I think we're onto something. I think we're onto something. It's just that the... Yeah, I don't know. We're onto something there, I think. Um, it's just that the if these little jaggies are the actual pixels, one, two, three, four, five, six, seven. Are there 7 or 8? Is that if we look at what we're using here, is it like 7 or 8 right now? No, right now it's 16, 16, so that looks still a little bit too jagged. Um, so I think that is, it kind of makes sense. It might be kind of close. We're on to something. I think we need to start color coding. Um, um, so let's like define uh, uh, okay, so this equation is definitely a point of interest where, um, yeah, that's definitely a point of interest where we want to make sure we keep our eyes on that, because I think it is potentially, I think it's potentially where our problem lies, but I'm not certain. But it definitely seems like that could be part of the problem. Now, well, these are distances, right? So I don't think we should be voxelizing our distances. I think that's why, by voxelizing our distances, or by truncating our distances become kind of step functions, and that's why we're getting that squareness that's aligned to what I would call the wrong axis. So I don't think we need fz, fy, fx, fy, fz as the minuses here, but it is giving us some insight as to kind of like where things are going wrong. So that's helpful. Let's keep on looking at. So we have this, and we've kind of figured out that this really should not be round, right? If we're kind of calculating what we're in, we want to take the xyz.x value, and we definitely want to floor it before we. Yeah, we want to floor it. So let's So we're going to use the floored X, floored Y, and floored Z here, because I think that's makes sense from the diagram we drew. And we can add a little diagram here since we, you know, why not, right? I'm going to turn the music back on and just try to enjoy myself here. Okay, so we got a little diagram here. And that's just what I kind of worked out for why we need to floor things when we're figuring out where we are, right, to get this math correct. Okay, so with that, I think that we have the correct pixel X, pixel Y, pixel Z, and I think we have the correct index. So we need to actually color code things based on that. Let's make sure we didn't screw up our multi-line comment and make sure that when we run this, it still works. Okay, so that still works. And let's... So since this function is really long, I think it'd be very nice to... We're not going to change this function name anytime soon. Yeah, I don't know what I like for this. Well, whatever, that's fine. So let's look where that's called really quick. Okay, so here's where we're getting that information. And the color should be this, like, color 4D value. That's the color output. And we see we're kind of setting it in a lot of places here. But where is, you know, the final decision for... So this is nested way too deep. So how are we going to figure this out? What is... What variables are we... I almost want this section to just be, like, included, because it's, like, so, it's nested so deep, and it's just the ray march loop, and it looks like shit being nested that deep. And we're using all this stuff. Yeah, I mean, it's not looking good here. This is kind of ugly as sin. Alright, we have all these cases where there's errors, and we are color coding. And, like, most of this is... So this is the one part where we actually have... okay, so this is where we are setting that color for the voxel. So let's just make sure that everything runs, that we haven't, like, tampered with it since we've moved around. Just a sanity check, okay. And let's... we'll do Vox 00 to Vox 00 C2 color 4D, right? And yeah, so we'll change this. So we're gonna comment this out, and we're gonna create a new function, and it's gonna be called. We're gonna call it equals Vox 00 converted to color 4D, right? So it's just, this is the input, and we're going to convert it to color 4D. And then instead of giving it the voxel value, we're just going to give it the entire voxel object. Which is a little bit, you could say that's a little bit wasteful, passing that entire object, but let's not, we're not going to worry about waste right now. Waste is like way in the future when we're trying to actually, when we have a final product and we want to optimize it. So with that, let's take that function and let's go. We're probably in the second degree functions right now, I think. So yeah, I can see why, like, now we're in first degree. Voxel object converted to fragment color. Voxel to color. Right. So this is naive. I always get naive mixed. So naive, how do you spell that? Is it N-A-I-V-E or N-I-A-V-E? Naive. Naive. So that is wrong. It's voxel to color. So I'm not going to use a word where I'm going to spell it wrong, because then I'm just going to search for the word, I'm going to spell the word wrong, and I'm not going to be able to find it. So voxel to debug color is basically what we have here. So we're going to say color 4D is a vec4. And then we just know the parameters are vox 000, and it's vox 000, and then it's going to be color 4D is the vec4, and that's C4D. So with that, you know, we might want to put the V4 in front like that, so that way we have a little bit of indentation and we can see our parameter list a little bit more obvious and still have this lined up aspect here. So we can do this, and so C4D lines up there, and then the vox 000 parameter lines up with its type. So that's kind of awkward, but you know what, let's roll with that. I think that's good enough. Okay, and commas off. Okay, so that looks good. That's a decent parameter list. And within here, we're just going to say that we'll like have some type of overlay, right? So we'll use the original. So originally we used this, and we'll use that as like a subcomponent, right? So we can use, we could use base, right? Okay, so this is our base color. Actually, it has to be a V4. And I think we might have more space, so we might actually be able to go like that. We'll do base color. Yeah, that way we have more room. Okay, so this is base color. So we can reuse that function we used previously. And now we just need some type of gradation where the pixel color kind of like I'm thinking it should be, maybe we could probably start off with something simple, where we just have like a checker pattern for the um, pixel x, pixel y value, and then actually, I think it would make more sense if we try to. So let's get the camera here. Let's try to do that. So with a ring, uh, and we want the ring to kind of be present on all layers, and the ring is like what? So looking at this, the closer towards the center we are, um, okay, so first we look to what face we're closest to figure out which two colors we're gonna what's gonna. Okay, so let me go back to here. So to figure out this. So we have to figure out which cross section we're closest to before we determine what color to use. So the first thing we could do is, before we even do that, we could just give it a solid color based on which, if we're closest to the X plane, Y plane, or Z plane, just to debug this, make absolutely sure we know what the hell we're doing before we continue. First of all, let's just return the base color, because that will have the original functionality that we had before and should not change the original image, and then we can kind of continue from there and keep on working. So we've already screwed something up, and let's see what it is. By now, I wish it would just zoom to no matching overloaded function found. Dimension mismatch. Oh, wait, because this is not a second parameter. That's wrong. So we're going to say that vec4 color 4D, and this is our output output. Okay. And then over here, we'll just say that color for D equals this. Right, well, we're going to make this a little bit more consistent and fleshed out a bit. So we're going to return color for D there. Okay, so now let's give that a shot and see if that will give us... so we still screwed something up. So this is kind of frustrating. C4D. Color 4D is not declared. Oh yeah, so CD4. So that's not a thing. So let's go over here for a second and go CD4 means, and CD4 means, and then CD4 type. CD4 is a typo of C4D. Okay, let's make sure we have C4D. Nope, we don't, so let's put that in here. So C4D means. C4D means. Okay, and then C4D is color 4-dimensional. X, Y, Z, W / R, G, B, A, right? Okay, so now that we have that, we can kind of go back to here, and we know that we made what mistake we made. So let's go into our code comments, and I know we made like a Control F index. So let's go to here and Control F index. So we have a typo fix. So if we do CD4, that is a mistake, and it's a typo fix. C4D. Okay. With that, let's go back to where we were kind of calculating those colors, and let's give that a run, and hopefully it actually runs this time. So let's... Okay, so now we got it working. I didn't see any changes. Okay. So... Okay, yeah, so let's... let's figure out the side that we are closest to, right? And it matters that when we're figuring out the side we're closest to, we just care about the distance from the center, kind of. This doesn't have to be exact. Well, it doesn't have to be exact, but let's... Okay, so let's do float 32. The distance on the x equals the min of the pixel x and number of npx minus pixel x, and +1, right? No, not +1. Well, if pixel x is, so if pixel x is 0 and number of pixels on the x is 16, then the last one would actually be 15, so actually we need a -1. Okay, so distance x, distance y, and distance z, right? And pixel x, and we're gonna need defines for this, right? So I just decided we're gonna keep it as simple as possible by removing the by just using a define. So we'll do define, and we need px equals vox000 dot voxel current dot px, right? And if I'm wrong, we'll fix that, but I think that's correct. So px, py, pz. Part of me just wants to make these lowercase, just because then I don't have to like worry about changing the cases. But then we won't know their defines. That would be kind of a bad convention. I just like because I could just copy from here and just instantly paste, and that would be a little bit easier to work with. But let's not do what makes it easier in the moment. Let's do what makes the code readable. So, right, we're only going to write it once. We're going to read it many more times than that. So let's not sacrifice readability for what makes it easier to work with in the moment. So px, py, pz, and let's line that up correctly. And I did kind of like keeping the note of what it is down here, though that is kind of cluttery. You know what? We're not going to do that unless this function starts to span so much space that we need to reference what these are from down here, because we can't see them up here. If it starts to get like that big of a function, then we'll add more visual clutter here to help us know what px, py, and pz are. But I think it's good just to keep it like this and reduce the amount of visual clutter. So we can check really quick and make sure that that is the sane value. And yep, we have it there, so that's good enough for me. Px's, y's, and z's. X's, y's, and z's. X's, y's, and z's. X's, y's, and z's. So that looks good. Now our math is probably wrong with the mixing of the floating point and integers. So we got to think about, first of all, min is definitely a function that takes floats. And this is a float, but npx is not a float. So we have to convert this to float 32. And we can do 1.0 here, but this needs to be converted to a float 32. So f32, npx, npy, and pz, minus pixel x, right, because we're going to invert that, right? We're trying to get the distance to the other edge. The distance to the first edge is really easy. It's just its value itself. And the distance to the other edge is we just have to invert that coordinate. So if pixel x is 15 and the number of pixels is 16 minus 15 gives us a 1, but we want to actually get a 0, so we minus. Okay, yep. So just double checking that, and that looks good to me. We can do a little sanity check, make sure I didn't screw that up. I think that's good, but let's just do it now so we don't have to worry about it later. Okay, so we're already fucked something up, and you know, that's kind of how do I say, disheartening, because it's like, this seems basic as hell, you know? Like, what the hell did I do wrong? And why do I continuously make mistakes that are so trivial? So we're actually missing a semicolon? 882. That was not what I would have expected. I would have expected something more... That's actually kind of scary, because that's... Okay, if it says we're missing a semicolon, but I don't see anywhere we're missing a... So that's very worrisome. That's like an error that you get it, and you see your semicolon, so you're like, uh-oh, that's not good, right? If we zoom in here, those are definitely semicolons. So that tells me that something about this line here is... Oh, it's our defines, right? So let's think of a way where we can write these defines in a way that's going to... I'm going to write it like this. Because I don't know. Okay, so we had the semicolons there. So let's give that a run. And we've still fucked up somehow. So let's take that, paste it again, make absolutely sure that that is... Okay, so let's see what we... This is getting way too long. It's wrong operand types. Okay. Float and int. So somewhere we're mixing float and int improperly here. And px is actually... Okay, px is actually not a float. And so we can actually do this. -1, and then the whole thing needs to be a float 32. So F32 like that. Okay, so let's try that. And now I'm just now I'm pissed. Possibly we're mixing signed and unsigned integers. That's my only other thought. No matching overloaded function found. Why? Because px is also a float. Also needs to be converted to float. So now we're gonna be like, fuck it. I thought that we wouldn't have to do this, but it's getting too verbose. I'm gonna end up outside of our bounds. So we got to do this. We're gonna define f as float, and then we can use this as a cast. And then we're also going to wrap that in a cast as well. And then we can... Okay. And since we're already using it, might as well. Okay, let's try that. See if... I really wish it wouldn't, like, move the scroll every time I try to rerun this code. It's getting really annoying. Okay, so there we go. So that is correct. Let's give that a run. Still looks as I would expect. But now with this, we can do the same thing, and we can do... we can figure out the closest side and say that if dx is less than or equal to dy and dx is less than or equal to dz, right? Else... And we're going to do the exact same thing 2 more times. And this should never execute. So we should never get here. I'm not going to add an error case just because I'm pretty confident that it'll never happen. And I don't want to be too paranoid with adding kind of like clutter. So dx, dy, and dz. And then y and z, and then dy, we're not going to compare it to itself, so we're going to do x and z. dz is going to be compared to x and y. So we've kind of done this math before, but let's color code everything. The first thing as a sanity check is the same amount of every color. So we got 4 cyan, we got 4 orange, and we got 4 yellow. So... So that's good. Now, the next thing is x, y, z, x, y, z, okay? We're using less than or equal to on both these sides. And these 2 colors in the 2 columns should always match. So cyan, orange, and yellow, okay? That matches. Also, we could just look for a visual pattern. So I see a little column here of 2, a column of 2, and if we go over here, and we just have this orange, but if we go up, right, we're going to, no, column of 2, column of 2, okay, well, I kind of see where this kind of connects to this, so this goes over to here, 1, 2, 3, Yeah, that's not the best way to look for a pattern. Yeah, but I'm pretty confident. I'm pretty confident that looks correct. So, with that, we're gonna just this base color. We're going to remove the base color, and we're just gonna say that color 4D equals vec4. And we'll do red, green, blue. Will correspond to each axis, just because I think that is the simplest way to do it. And we'll put, we'll use an A for alpha, and we'll actually just, we'll actually, you know, we're just gonna define elp for alpha, and that's 1.0. And then undef ALP. And the reason why I want to do that is so that we can, when we're writing these, I don't want to get confused about, this is what we actually care about. We really don't care about this alpha component, so I just want to be able to put it off there and then be able to focus on these three numbers when I am looking at this. So taking that, we can paste it a few more times, and then we'll change around the values, right? So this is red, green, and blue, respectively, for each of the axes, right? So X, Y, Z, red, green, blue, and let's give that a shot and hope we didn't screw up anything, because I'm getting sick of my screw-ups. Okay, cool. So we have wow. So that's interesting. That's very jagged. There's a lot more jaggedness here than I would have thought. Like, we're getting, so let's try to run this. And okay, so this is that jaggedness you're seeing is where we're hitting the where the camera is hitting, right? So the camera is kind of moving back and forth, and it's slicing in, and when it slices in, we get these jaggies wherever the slicing in is happening, right? So that actually makes sense, why we would have those jaggies. That's kind of cool, because now we can see the difference between where the cross-section cut is happening and where the exteriors of the geometry is happening. Now that's kind of pretty obvious, which is kind of cool. So I kind of like that. That's nice. But holy crap, now we got like little artifact. Oh god, the artifacts are getting way out of hand. But it's not like, it kind of feels like we're taking steps back, because, you know, first we saw these artifacts, and now we have like these little artifacts here. So now it's kind of like you could feel like more demoralized, because you're like, shit, look at these new artifacts. But don't think of it that way. Think of it as, oh, here are some artifacts I was not seeing before, because we weren't putting color information on the faces, right? So it's not that these artifacts are new artifacts. They are old artifacts that we could not see, right? For an exaggeration of that, if we colored every single face black, and we also colored the background black, and we didn't use any lighting, we would just have a black screen. You wouldn't be able to see anything. You wouldn't be able to see any artifacts, but you wouldn't be able to see any meaningful geometry either. So, okay. So with that, let's go in here and kind of try to refine each one of these pieces, right? And try to so we want to eventually use this base color, but just use the distance on, so if x is the closest plane, then we want to use zy. If the x normal is the closest, if the x-plane is closest, then we use the z and y, right? So we want to figure out the texture on the face of this. So let's, so x is closest. So we could make a note here. So, you know, the x dx equals x plane equals it's going to be, from what I'm looking at, it's going to be, we're going to look at it from the top down, or no, we're going to look at it from the side. So it's y is our x value, and then z is our up and down value. Yeah. Okay. And for that, let's, we just have to do like this min kind of a thing again. So, it's actually like the min yz. That's kind of what this is, min yz. F. So let's just copy that, because we're gonna need it again. So we're only gonna need one of these, and it's gonna be, we're gonna call it min yz. Min yz. And we just need to take the, do we want to use the distances? Yeah, we still want to use the distances, right? Because, yeah, so min yz is going to be distance y, distance z, like that. And actually, so we don't really need to use the defines. We have enough room where we can, yeah, we don't need that. So min yz, and let's just do, I'm going to call it min 2D. And the reason why I'm going to call it that is I'm going to declare it over here. So float 32 min 2D. M2D. Minimum 2D. And the reason I want to do that is just so I can... Actually, I'll keep that kind of like commented out there. So let's see, for the dy, so for the, if the y plane is the closest, if the y plane is the closest, then we want to look at x and z. Okay, so dy equals y plane equals x z. Okay. And so if we are doing x and z, the min 2D equals the min, and we have y, so we just consider the other things. We don't have to do it in the very specific order. Min doesn't care about order, but we should maintain the correct order for visualizing, looking at the plane, and thinking about what's x and what's y. So for y, it is x and z. So dx and dz. Okay. And then for our last one, for dz, so dz equals the z-plane equals just an x and a y, right? Because we're looking top down, and remember that z is our kind of like our extra axis. We want to do all the math normally. And z is just like a projection out of the screen. So if we're already looking at a top-down view, it's normal. So it's just x and y like that. Then we can comment this out. And our min value is going to be min 2D equals the min of the dx and the dy, right? Okay, so let's take a look at that and just color code dx, dy, dz, and make sure that everything looks balanced. So I see this orange and this yellow, and this yellow, that kind of concerns me. Pattern-wise, the patterns are like, why are there two of these? But then there's two of these like that. So let's do a quick checksum and make sure there's the same of every color. So we know there's the same of these colors over here. So let's just count the colors over here. So 1, 2, 3, 4, 5. There's 5 cyan. There's 5 orange, and there's 5 yellow. So that's a pretty good indicator that everything is balanced and we've done the math correctly. Now we can look at, I believe we have 3 different possible ways that we can combine, not permute, but combine the x, y, and z. So, so I think all of our permutations are here, right? We can have cyan with orange, or we could also have cyan with the yellow, or we could have orange with yellow, or we could have orange with cyan. Do we have orange with cyan? We do have orange with cyan. Last week we could have yellow with cyan, or we could also have yellow with orange, and we do have yellow with orange. So we have all the possible combinations of, we have 3 choose 2, and we have all of those combinations. So if we go into Google, I believe we can do 3 choose 2, and we should get the value 3 out of that. Yeah, so 3 choose 2 is 3, and we have 3 different cases, and we have 3 different unique values, and we're choosing 2 out of them, right? So here's the 3 different values we're choosing from, and then we're choosing 2 out of those 3, and so the branching logic reflects the combinations that we're doing. So that makes sense. So with this min 2D, we have to remember that this is in terms of pixels, and when we're trying to do a gradation, we're going to have to take whatever the highest values out of the number of pixels x, number of pixels y, number of pixels z is, right? So we're going to take, we're going to say that F32 NP for number of pixels equals max, and then NPX float NPY, and then float NPZ, number of pixels in a tile, right? And let's make absolutely sure that NPX is what we think it is. So if we look at NPX over here, number of pixels in a tile. So we are correct that NPX is the number of pixels in a tile. So let's go back to our, if we want to remember this, we had like a is it M3D? It was not M3D, so let's go to our typos section. We want to be able to get back to places easily, so if we don't remember it correctly, we should have M3D. We wanted, that's not what it was. What was it? I don't know what it was. It was, Voxel to color debug, and that's going to be C Vox So we're gonna hashtag that with Vox bug color, and it's Vox 000, and we're converting it to a color 4D, right? So let's see if we can find it just based on that. And yeah, we're back where we wanted to be. And it's M2D is what we wanted. So Control F And we can actually put the ats over here. So we'll do like, so we have like a at Vox bug color, right? Yeah, at Vox bug color, and this is a typo fix as far as I'm concerned, and it's M2D for, right, so we can find that variable a little bit quicker. M2D for minimum 2D. Okay, so now from here, the number of pixels, we want the max to create the gradient, and F32, the percentage equals the so this minimum value is always going to be halfway, right? So if we want it to be a full percentage, we want to multiply it by 2. And then we're going to divide by the number of pixels. And that's going to give us the gradation, right? And is that gradation going to be darker in the center or darker on the edge? Well, on the outside, it should be kind of a blackish. And then in the center, it's going to get brighter. Now, we might want to change that around later, but I think that's fine for now. And then what we're going to do is we're going to take this percentage, and we should just be able to, well, no, we can't quite multiply color 4D by that because we have this base color. Color 4D isn't anything yet. So we're going to say that color 4D equals vec4. And we're going to take the base color.x multiplied by, right, we're going to do this very verbosely, base color.y times the percentage, base color.z times the percentage, and then we're just going to keep the, base color dot xyz w times 1.0, right? We're not going to change the alpha, right? Okay, so that looks good to me. Let's give that a shot. Hopefully we didn't make any syntax errors. We probably did. 90% of the time it seems we do. So let's try to figure out what we did wrong rather than look at it right away. So this is the extra bits of code we wrote since. And what could have we screwed up here? So max, our float cast is missing, right? So let's fix that. So we gotta define float again. So f float, and then undef f. So we gotta redefine those. Okay, so that's good. Let's give that a shot, see if that fixes it, or if we still have a problem. Okay, so we still have a problem. Let's look for what else could be wrong here. Max, float, npx, npy, npz. So the casts look correct here. We have the semicolons, f32. Percentage. Is this a float 32? Yes, it is a float 32. Dividing by a float 32 gets a float 32. This vec4 constructor. Base color. Is base color a vec4? It is a vec4. And percentage. The commas look like they're in the correct place. So now I am kind of stumped, and that's kind of demoralizing. Like, why can't I see what is probably, like, very obvious? I don't know. We're going to take a look at it, though. Let's go look at what the compiler says that I screwed up. Max, no matching overloaded function. So... oh, right, because we can't do max with 3 things. So I'm getting really fucking sick of max not being overloaded for 3 things. So we're just gonna say max. I know we wanted a max function that would we're going to call it max3 like that. Yeah, let's just call it max3 like that, and it's going to function just like a normal max, except it takes 3 parameters, right? So let's scroll all the way up into our next degree highest functions. Let's not worry about the exact order. But okay, so this is infinite degree. You know what? It is a utility function, and therefore I'm fine with it being in the infinite degree. Let's not make a third degree for this. Max of 3. Okay. And yeah, because I'm just getting sick of it not being overloaded like that. So we're going to do the same thing where we're going to use the same convention of max is just always float in GLSL. So we're just going to keep that part. And we'll just do float 32A, float 32B, float 32C, right? I'm just going to keep it dead simple. And return the max of max A, B with C, right? Alright, so we just want to have the A, B, and C kind of like in the correct linear order when we do this to write it kind of as plainly as possible. And there we go. We have our little utility function because I'm getting really sick of that. Especially since we're doing things in 3D, you'd think you would have like a max function for two things, but I guess this is shader code, so I guess it was designed for 2 dimensions. Okay, so that I think will fix it, but we could have made a mistake in our function declaration or whatever, so let's just give that a shot. And okay, ooh, that is kind of fun. That is, I'm liking that. That is, and we can actually see where the artifacting is happening, right? We can see the places where we are expecting a so first of all, this looks badass. This looks cool enough to where I think I want to take this code here, and we're gonna update the source code so you can have the source code. So I'm gonna hit the save button here. So if you go to it's a little bit indirect, so I'm going to update all of the URLs really quick so that wherever you go, you're going to get the updated source code. So I think this is a good checkpoint. I think this is a really good checkpoint. So I'm going to update the reference URL on pastebin.com. So I'm going to go to tinyurl.com/sdf-013. And on Pastebin, we're gonna put this code up there. So if you wanna hack with it, you can do that. So let's go all the way down here. I'm editing this off screen, but once I edit this, you'll be able to have access to the updated code. So save that. The code is kind of long, so sometimes it makes scrolling to figure out where to hit the save button. It makes that kind of annoying. So forgive me for the delay, because I'm like, I don't even know where the fucking button is right now. Well, let's hit edit. Control A, control copy. Okay, so is this my source? Yeah, that's my source. Okay, and save changes. Okay, so that's updated. So yeah, so now if you go to tinyurl.com/sdf-013, that will get you to the source code. And then within the top of the source code, it'll tell you the URL to this actual shader. The live demo is in the top of the source code. So if we actually look at my source code here, and we kind of scroll up, you're going to see I have like a nice little explanation of everything we have, right? So this is where you're going to go for the stream, and that's not really for you if you're watching the stream. And then we have the tiny URL, which is a little bit easier to type. So SDF SDF-013. We have the exact paste bin URL here. And then same thing with the actual demo code. So the shader toy demo code, you could do SDF-013/demo, or you could do this exact shader toy URL, which, you know, you're not really going to remember that. So that's why I have these exact URLs, and then I have these shorthand URLs. And I think that I'm going to update the summary here. Debugging artifacts in edges of voxels by color coding each pixel of each voxel, right? And then maybe a little bit, nope, my voxels are just 3D tile maps. 3D tiles. So we're gonna make a note. So think, that's not correct, that needs to be okay. So think 2D tile map with an extra axis, right? So in case you're confused and you're looking at this and this doesn't make sense, it doesn't make sense as a, like, what the hell, voxels? Voxels don't work this way. Well, they work this way for my code, right? So I'm just doing the math for everything as if we're doing a 2D tile map and just adding another axis onto that. And that's just because I think it'll be easier to think about and easier to reason about the math. And I think so far, I think I've proven that just from what I'm seeing. So let me. I'm going to save this. I'm going to update the paste bin one more time since I kind of made that change. So I'm going to hit edit. And then looks like I got to wait a little bit. Control A, Control V, and then we'll save the changes. Okay, so now the newest changes are up for SDF-13, and I'm going to switch over to doing SDF-14, just because, like, this pattern that we have on screen looks really badass, and it makes it like a good checkpoint to where if I put all these videos in a nice collection, I want like a nice screenshot for everything, like a nice distinct screenshot that kind of shows the visual progression of how we got to where we're at. And this looks really cool. So I can explain what we're seeing here in case you're new to the code. So each voxel tile has been assigned a uint32 value that directly corresponds to a RGB value, and that's why the voxels, that's how we're getting the color from the voxel, right? And then the different shading, right? The shading is based on how close the exposed pixel on the voxel is to the edge of the voxel, right? This pattern right here, this green section you're seeing, is the actual camera slicing in to the voxel, right? So the next thing, what do I need to do next? So I kind of explained that, and there's something else I wanted to do before I went to the next thing. I can't remember. But yeah, that, oh yeah, I just wanted to show you where these colors are coming from in case you're new to this code. So over here, we've kind of given these hex values. So we have C for cyan, Y for yellow, M for magenta, L for lime, and O for orange. Capital, I think of capitals as yelling. So the capitals are the bright cyan. Lowercase c is a dark cyan. Uppercase Y, yelling. A bright yellow. Lowercase y, not yelling. A dark yellow, right? Uppercase M is a yelling, so we use a bright magenta. Lowercase m is not yelling, so it's a dark magenta, etc., for all of the other colors. So once we can make these defines, we can start to color a tile map. So we're abstracting our tile map or our voxel map as a whole bunch of two-dimensional tile maps that are just stacked on top of each other. That way it makes it really easy to reason about and abstract in the data, right? So this is a two-dimensional tile map, this is another two-dimensional tile map, this is another two-dimensional tile map, and they're just layered on top of each other in order. So this is z equals 0, this is z equals 1, this is z equals 2, z equals 3, z equals 4, z equals 5, etc. And we just keep on going down through the different stratas of the voxel tile map. So with that, the underscores are a define for 0. So we have this, we can easily visually parse the data because since the dash is a very small character that doesn't take up much space, the luminosity between these underscores and these characters creates enough contrast to where we can kind of visualize what the tile map looks like by just looking at the data, right? So this is kind of the object we're trying to create, and it's not really anything fancy. We're just kind of like debugging right now. So it's not any kind of fancy type of design yet. It's just a put some pixels in 3D space or put some voxels in 3D space and just make sure that everything kind of looks correct. And yeah, I think we're really close. Yeah, so that's an explanation of kind of what's going on there. I'm going to make absolutely sure that all of this runs. So I'm going to cut and paste into the shader toy, and then I'm going to save that. And actually, I'm going to done developing this for today. This is a debug view of each voxel. Each voxel is a unique. So you can't see this, but I'm updating the description on shader toy. Let's go there. Okay, so done developing this for today. This is a debug view of each voxel. Each voxel is a unique base color. Then we shade based on how close the voxel surface pixel is from the edge of the voxel. I define a voxel as a 3D tile, 2D tile map, plus one extra axis. So that's a good explanation there. So I updated the code there and made sure that so that is updated, and just making sure that that's all up to date. Let's take this, paste it into paste bin one more time to make absolutely sure it's updated, and then we're going to move on to a new session. But I'm also going to take a break, so I'm probably going to stop the stream and start it again in maybe 30 minutes because I need to get a little bit of food, or start some food at least. And yeah, so let's update that, save changes. Yeah, so I'm gonna get some food, and I guess I could, I'm gonna start a new stream because I'm gonna like make new URLs and stuff and get like my project space set up for another stream where we kind of build upon what we've just done here. And you know, I just need a break, right? So I also should probably go for a walk by now because it's almost dark. Oh god, it's snowing. I really don't want to go for a walk, but I think it's good for me. So see you in the next one in maybe 30 minutes to an hour. All right.